Okay, welcome all of you to the week 3 webinar for our online statistics class. And hopefully you're starting to get into the groove of things. We've now had 2 full weeks. And in particular, you've had your first exam. And by the way, as you go, if you can give me feedback, if there's something that, didn't go well or whatever and could have been done better, I want to let you know that I've been teaching online for like 20 years, but this is new to me in the semi-weekly or bi-weekly exam. So I haven't given an exam every other week before. I used to just give 2 exams and I'd have them proctored and you go to the library. With COVID, that doesn't work. So I'm trying this as a new thing to do these little like mini exams every other week. So you're going to have 6 total mini exams, which is very different than, like a big exam. There are no big exams. So just let you know that that's how it's going to work. And also I want to let you know this is the first time I ever did a math-based exam where it had fill in the blank questions. I mean, not fill in the blank, but essay questions. Were you able to, because I'm not a student, so I can't see what you're seeing. When you saw my comments, were you able to look back and see the question or not? So you can see that? Okay, again, it's hard for me. I only know from you guys whether you can see it because I am not a student, so I don't get to see what the student looks like that way. And there's this whole interactivity between Canvas and my open math, and so I can't do a preview, unfortunately. So if there's ever anything that doesn't work, let me know, and I'll fix it. That's the good news. Is I'm pretty good with text, so I know how to fix things. But this was the first time ever doing this kind of exam, so I want to make sure it worked. So it worked for everyone? Okay, and I do want to let you know the problems were randomized, all of them. So all of you got a different exam, but I did my best to make it so that all exams were the same difficulty and they all covered the same topics. So if you and your friend got different exams, hopefully that they were the same difficulty and basically the same ideas, even if the questions were all different. So just let you know that that's how this one works. So it was new to me and it seemed like it worked. And if you hadn't looked, yesterday was my grading day. Normally it'll be Tuesdays for grading day because normally I teach Mondays from 9:30 till 4 o'clock without any break, basically teaching of office hours. So I'm not grading because I'm teaching. And then Tuesdays is my not busy day, but of course, yesterday, I think you all know why I wasn't teaching yesterday. If not, then I don't know where you've been, but it was MLK Day. So we were on official vacation, although I did grading instead. So that was the grading on it. I'm pretty quick at grading, but Mondays are usually too busy for me to do anything. Just let you know that. Okay, except maybe for an hour early morning. So let me share my desktop and talk about what we're going to be doing in this webinar. Okay, and just a minute. Chat up. Can you all see it? Okay, so here's the plan of the day. As always, I'll start out with any questions that you might have. And I do want to let you know that any questions that you have about the project that you want to type out or whatever, the Project One discussion board is the way to have that conversation with me and each other, actually. And if it's with your partners, you can do your private email and talk about however you work. But if it's more general for the class, then it's the project discussion board is the way to go. If you have questions about the homework, the regular assignments, or the discussion posts, that's the Q&A. If it's a personal question, that's email to me. Okay, that's kind of how the questions happen. And then of course, anything's up for grabs right now because this is Q&A time. Then we're going to be doing 2 chapters. And as I promised, hopefully you'll agree. Chapter 3 was really brutal. I don't know if you agreed, but most people do. We have 2 chapters this week, which I think is a lot easier than just 1 chapter last week, believe it or not, because they're very kind of step by step. And the 2 chapters are, the first is discrete distributions. And discrete distributions are when you can list all of the answers. That makes it a discrete distribution. So there's lots of examples of that. Things like if it has the word how many, for example, it's almost always discrete, whereas how much is almost always continuous. So we'll talk about that. We'll talk about the expected value and the standard deviation, which is really, really important because it gives you an idea of whether it's a good idea and how good the idea is if you're doing something, gambling or whatever. It talks about that. And then we'll get into the binomial distribution. And that's very important for the yes/no question. So if you're going to do a survey where it's a yes/no question, which you're not allowed to do in your project, by the way, but if you can do a yes/no question survey and you want to find out a probability that that many people would say yes, that's a binomial distribution question. So that's the main thing. And it doesn't have to be people, it could be whatever. Then we're going to get into chapter 5, which is continuous distributions. And that's more of the how much, things like how much do you weigh, or how much time did it take you? So where you can't list all the possible amount of time it could take. If it say takes between 1 and 5 minutes and you're not doing any rounding, okay, because it's a number line piece. So we'll talk about what continuous distributions are. And then in chapter 5, it goes through the easiest distribution and really the only distribution in this class that we can do by hand. And that is the uniform distribution, which comes up a bit here and there. It's not the most important one. That'll be next week. But this week, we're going to be doing the uniform distribution. That's when everything's the same. Okay, and the uniform distribution is important. And we'll see that. And we'll realize that you probably never guessed, but area of a rectangle is something really important for finding uniform distribution probabilities and doing that. So we're going to be doing area of a rectangle a lot. And we're also going to be looking at algebra. Some people don't like this part, but this is one of the few places in the class we actually have to do a little basic algebra, very basic, nothing harder than beginning algebra. But you're going to have to, solve an equation that is, 3x plus 5 equals 7 or something like that. So you're going to have to do that kind of stuff. This is kind of an algebra chapter. And then we'll talk about the mean and the standard deviation of the uniform distribution. And those are formulas. So a question was, how do you define the term distribution? So the idea is that if you're doing some kind of study and you're looking at all the different answers that could happen, and you typically look at the kind of proportion of that one could happen, proportion that one could happen, probabilities, and you graph them all typically, then the distribution is that picture. Okay, so that's really the distribution. It's the function, it's the probability function for whatever you're looking at. And for the uniform distribution, it's the easiest because the probabilities are all equal, so it's just flat. A normal distribution is that bell curve looking thing. I don't know if you remember that from the last chapter, chapter 2. So that was a normal distribution. There's others too that we'll have throughout this class. So that's the word distribution, if that helps out. Okay. Any other questions about anything? Distribution's a great question. Any other questions? Okay, if there aren't any other questions, another reminder, if you have not found if you don't have 3 in your project group, see if you can get a 3rd person. If you don't have if you haven't even done it, you need to get project partners. That's important. And again, the project discussion board is good. You can also put in the chat now if you're looking for a partner, and maybe someone will grab you. So that's a possibility, but project's really important. And this is the time when you should really be thinking about planning your projects, posting your plan on the project discussion board, and I'll take a look at it and typically help you modify it so it'll work better. Because again, this is, you haven't done this before, so I don't expect you to have a perfect plan on your first try. But I do expect you to have a good plan after working with me for a week, or Brawley, or whoever you're working with, to get a good plan. Okay. So that's just a big note. That should be the focus this week. Let you know there's no exam this week. So exams are every other week. There's no exam this week, and that's, you know, one reason why 2 chapters make sense this week. Whereas next week, you'll be working on your exam and your project. It's actually, I think next week is probably the easiest of all the weeks in terms of new content. But you got project and an exam, so it's not an easy week at all. Okay, so if you don't have any questions, and again, feel free to ask any question throughout the webinar about anything, and I'll answer. You can put in the chat box, or you can talk. If you talk, it gets recorded. If you put in the chat box, that doesn't get recorded. And I try not to say names when I read the chat, just in case you have some kind of privacy issue. Okay, so let's look at discrete and continuous variables. So let's talk about a couple things. So a discrete variable, let me make it good old red because it's important. A discrete variable is a quantitative variable. Who remembers what quantitative means? Very important for the for your project. Yeah, numbers. Okay, so a discrete variable, first thing it has to be talking about numbers. So it's a quantitative variable whose set of outcomes can be displayed as a list. Okay, typically you put all the outcomes in a table and you put the probabilities below that. And that's why it's a table, because it's got 2 columns or 2 rows, however you want to make your table. Okay, so that's the main thing, is we can make a distribution table. And what we want to be doing is we want to be looking at these discrete probabilities and answering important questions. So I have an example. And it's the following. Okay. And if for some reason you can't see it, let me know, because I don't know what you're seeing. So I'm reading it. Hopefully you can all see it. Is a car salesperson gives out a $10 gift to every customer who drives a car. Okay, have you ever heard of something like that happening? Yeah, they do that. Okay, it happens all the time in business, right? Sometimes you'll walk into a shop and they give you a piece of candy or something, right? So whatever it is, that costs them, the owner, money, right? And they're hoping that you're going to buy that car or buy whatever they've got. Okay, 12% of all customers who test drive a car purchase the base model of the car, resulting in a $200 commission for the salesperson. 8% of all customers who test drive a car purchase the deluxe model of the car, resulting in a $300 commission for the salesperson. So do you think that this is a good idea? What do you think? If you were, if that was your job, selling cars, do you think that gift idea is a good idea? Do you think you're going to make money in your job? That's the main thing. And how much money you're going to make, right? Okay. And some of you say yes, right? But really, you don't know until you've done the math. And that's what we're going to have to do, is we're going to have to do the math. So it's a very typical thing people do in business, is they decide whether or not it is worth it to give something away. And let me give you some other give somethings away in something you may not even thought of giving away, but advertisement. When you advertise for your company, It's just like giving a $10 gift. What you're doing is you're giving the, the website or whatever you're advertising at money to put your ad on. It's no different than giving someone $10. Does that make sense? Pretty much happens in most businesses. This is a biggie. And we want to find out, is it a good strategy or not? So what we're going to have to think about is a couple things. One is, if this was your business, this was your job, and you did this for months and months, are you going to make a good salary or not? Does that make sense? Is it going to be worth it? Is this a job that is going to bring you money? Okay, or maybe you're going to lose money. If you're going to lose money, don't even think about doing this, right? And if you're going to make, a penny a person, that's probably not enough, right? Because it doesn't pay enough for you. So what we want to do is we want to say, in the long run, with many, many customers, on average, how much money do we expect to earn per customer? Does that make sense? Any questions on that idea? So that's like the big topic of this chapter, is to be able to answer that question. So now let's get into it. So the first step is to make the probability distribution table. So I've got a table written. And let me show you how that works. So a probability distribution table is a table. Hopefully you know what a table is. It has 2 rows, and you can do columns if you want. I'm doing rows because it fits better on this particular screen. That's why I did rows. But table, rows, columns doesn't make any difference. Where the first row is the value. In this case, what is the salesperson interested in? Right? In business, what do you always want? Commission, but even more important. Yeah, commission minus revenue. What's commission minus revenue in one word? Waiting for a word. It's the biggie. Profit. There we go. Profit. So hopefully you all know that profit is what it's all about in business. Okay. By the way, repeat customers does work in some businesses. If you're selling new cars, repeat customers don't happen much. People don't buy a car every week. So that probably isn't it. Profit is really what you want. So what we're going to do is we're going to let X correspond to the profit. And then the next row of a probability distribution table is P of X. Now we've seen this notation before. What does that represent when you write P parenthesis X and parenthesis? That's the probability. So that's the probability of that individual profit happening. Notice that this only works like this for discrete variables, because we need to list out all of the different profits that can occur. If you can't list them out, you can't put it in a table. And we will today talk about what to do in that case. And it won't be tables, it turns out. It'll be graphs. Okay. So then what you do is you say, well, what are the different profits that can happen under this scenario? Any questions on that? So in particular, let's take a look, and let's look at if the person, again, if we read the question again, 12% of all customers who test drive a car purchase a base model of the car, resulting in a $200 commission. So if $200 is the commission and we want the profit, well, we're giving a $10 gift to everyone. And the profit is the commission, sometimes called the revenue, minus the cost. And 200 minus 10 is 190. You might be able to do that in your head like I did, and if not, you're always allowed to calculate it. So let me stop. Any questions? Any questions on how I arrived at that number 190? All right. Then 8% of customers purchase a deluxe model and they get a $300 commission. They still have to give the $10 gift certificate out. So that's going to be 300 minus 10, which is 290. Any questions on this? Is that all that could happen? You can make 190 or you can make 290? Yeah, most of the time, the customer is going to say, oh, sorry, I don't like the car. But I like your gift, thank you. And if that happens, then what's going to happen is you're going to lose $10. You're going to give away $10 and make nothing. So it's 0 minus 10. And 0 minus 10 is negative 10. Any questions at all? Any questions at all on finding the values of X for this example, this car salesperson example? Any questions? Okay, so the next thing we need to do is find the probability of X. And that is basically given. So the probability, remember 190 meant just the base model of the car. And we said there was a 12% probability that they're going to sell the base model. Any questions on that? Just a note, and this is very important, percents are terrible when it comes to calculators. So whenever you're creating a probability distribution table and you're given percents, you need to turn those into decimals. And hopefully you all remember, you turn into decimals by moving the decimal place over 2 places. And that becomes a 0.12. Any questions on that? Very basic math. Okay, similarly, 8%. Okay, if we move the decimal over 2, that's 0.08. All right, one of the things about probability is that if you add all the probabilities up of anything that could possibly happen, what do you always have to end up with? What is the sum of probabilities? It's always 1. Okay, so that's important. So what I do to find the probability to get that 0.8, but I'll show you how I got it, is the probability of losing, probability of negative 10 is equal to 1 minus the probability of the rest. So the probability of 190 minus the probability of 290. Any questions on that little calculation right there, that setup? And that's 1 minus, probability of 190 is 0.12, and then minus 0.08. And you can do it in your head, you can use a calculator, whatever it takes, but you need to be able to do the math, and you get 0.80. And that's how I got this probability, this last probability. So if you're ever given all the probabilities except 1, you can always get the last one by adding up, basically adding up the others and subtracting from 1 when you're done. Anyone have any questions about how I came up with this probability distribution table? Okay, so it's nice to have a table. It's kind of cool to look at the probabilities, but if that's all we had and it's all we could do, this is worthless. Do you agree? Now it's time to answer the important question, which I mentioned a little while ago, and now I'll mention again, but now I'm going to put it in red. Oops. Yeah. And that is, if many trials are done, then it is very likely that the average of the trials will be very close to the expected value. So the expected value gives that number at which it is likely to average that number over many, many trials. Okay, which is really what's important. Okay, or one of the main things that's important. There's a formula for it. You don't have to actually use the formula. Do you know why you don't have to use the formula? You don't know why you don't have to use the formula? Any guess? No, it's definitely not always equal to 1. You're not always going to get a profit of $1 in the long run. Does that make sense? All right. The hint is it was my job to use the formula. That's your hint. I don't see y'all jumping in because I coded the calculator to do it for you. Okay. Yeah. It's not the information is always given, but the calculator is already given for you. So what we need to do now is we need to go to the calculator. And hopefully it's okay. You all know how to get to this calculator now? It's the same calculator. So throughout this entire course, this is the calculator we're going to use. Again, I'm trying to make it simple. By one calculator, it's always what you use. There's again 25 different things that you could use. And we need to use one of these for what we want to do. And hopefully I tried to make it obvious when I program this calculator, which number do you think is the right one to use for what we want, given that what I just said on the last screen? Of course, you have to remember that. So you have to remember what everything is called, by the way. Yeah, number 6, because what we want is the expected value, which tells us that if over the long run or many, many trials, it gives you what it is the outcome or the average of all of the outcomes is likely to be close to. Any questions on that? So if I click on expected value and standard deviation, it has a table. Okay. This table happens to be vertical, but hopefully that's not a problem for you. Now you got to remember there was a 190. There was a 290. There was a negative 10. Okay, if you don't remember, that was all there. 190, 290, and negative 10 were the values of X. And then the probabilities were 0.12, 0.08, and 0.80. So I put 0.12. And 0.08. And then and 0.80. It looks like you get an 80% chance of not even selling anything. It looks like a bad idea, doesn't it? If that's all you thought about. But let's find out. Okay, so then the calculator is going to do that math formula for you. It's going to do standard deviation, which we'll talk about in a minute too. So then I try to make it easy. You have to hit the calculator button. Hopefully you know how to do that. And that's it. Any questions at all on using this calculator? Okay. Definitely, practice. That's how you get good at using the calculator. Okay, but I tried to make it easy as I could. And if you have any suggestions, let me know. So the expected value is 38. So let's go back. So our expected value is 38. And since expected value is what the average is likely to be close to, and remember, average is the same thing as the mean. Do you remember that? So that's why you'll often see mu, because that's the letter we use for mean. to be used for expected value. So if you use a single letter for expected value, mu is the letter you use. Sometimes you'll use EV because that like reads better for expected value. Easy to remember, EV means expected value, but also mu. Okay, so the expected value is 38. So what does that tell us? So, and you are responsible for being able to do this. I will be asking you to write a complete sentence to interpret the expected value. Got it? And let me mention something really important, by the way, and that is I put in red many, likely, average, close to. Do you see that? All right. If you don't want to lose points, you better put those words in when I ask you to answer the question. Okay, that's a promise. And if you want to get points, put words in, put those words in. Okay, if you don't, then you're going to lose points. Got it? Okay, but don't just like write this. We need to do it in the context of the question, which is this car salesperson. So what we can say is the interpretation is that, so it's not trials anymore. You don't call people trials in this case. Here, it's customers, right? So if the car salesperson, let's do this. Has many, there's that word many, because again, we need that word many. Now it's not trials anymore. What does he have many of? Or she? Or they? Customers, not potential customers, but customers. Then it is very likely that, okay, so now it's the average of what in salesperson words? And I mentioned it's the big word in business. Profit. That the average profit will be close to. And now it's not 38, just 38. What are the units here? It's not 38 feet. It's not 38%. It's profit, that's a hint. Dollars. Yeah, it's $38. $38 will be close to $38 per customer. All right, so what do you think? Is this a lucrative job? Do you think salesperson is making decent money? How long do you think it takes to show someone a car? I'm not a car salesperson. I don't know if any of you have done it. Think an hour or two? Okay. It's funny, you know, every class gives me a different answer. So if it takes an hour, then the car salesperson on average is making 38 bucks an hour. Okay. Not terrible for a job that has no education, you know, needed. My brother actually did it in, I think it was in between high school and college when he was 18, and he was a car salesperson as a summer job. I don't know, you decide if that's lucrative or not. Okay, so and again, that's up to you. You have to think about how long it takes to see a customer. Any questions on that? Okay, so then we also want to know is how should the salesperson react to the standard deviation? So again, on average, in the long run, the salesperson is likely to make close to 38 bucks an hour. Okay? Not terrible, not, not going to get rich on it, but better than minimum wage, right? Even in California. Okay. On the other hand, the standard deviation, which again, you don't need to know the formula for, but you do need to know how to move your eyeballs when you have the calculator. And the standard deviation is, I'm just going to round in the nearest whole dollar, is probably good enough. 98 bucks. Okay. Standard deviation is $98. And standard deviation, by the way, who remembers the letter you use for standard deviation? So that's a good idea. Is the standard deviation a sample or population? For what we're doing today, it's a population standard deviation. Because there's no sample taken here. Do you see? We're not looking at 50 customers and seeing what happened. Do you see? This is a theoretical everybody question. Do you see that? So that's why it's population. Yeah, so we're going to use the letter sigma, which, by the way, let me show you on Google. If you're using Google Docs, you go to insert equation, and then you go right here, and there's the sigma. Sigma was equal to 98. Is that, let me make it a little bigger. Is that a large standard deviation or a small standard deviation? Given that on average, you're likely to make close to 38 bucks and the standard deviation is 98. What do you think? Yeah, this one's large. So what that says, let's write this down. The standard deviation is quite large. All right, now what does a standard deviation measure? We've learned about standard deviation already. Remembers? Yeah, above or below, by the way. Right? So it kind of gives you a kind of an average distance from the mean that these profits are going to be. So this standard deviation is big, which means that a lot of times salesperson is not going to make anything. Do you see? So what that means, therefore, the salesperson needs to have a large amount of money in the bank, because there will likely be dry periods. And dry periods meaning that there'll be periods at which not going to make any money, is actually going to have to lose money. Do you see that? So that's how you would interpret this standard deviation. Because it's large, that means you got to do that. By the way, other areas besides car salespeople, real estate is another one. Realtors make a lot of money when they sell a house, but it could be a long time before they actually sell one. I don't know if anyone's done real estate, but that's typical. Whereas things like supermarkets, you think they have a high or a low standard deviation? Yeah, theirs isn't as high. Okay, and also they have fast, especially if you look like per hour or something like that, for an hour of customers. There's not much standard deviation. Okay, how about casinos? Casinos have a high standard deviation because once in a while the person wins the jackpot. Do you see that? So that's going to, remember, outliers boost up standard deviations. Any questions at all on this example? Any questions? Question?
I was going to see, is there any specific wording we have to give when we're describing the standard deviation?
Well, you should talk about large or small. So that, that depends.
Okay.
But don't always say large because it won't always be large. Could be median or moderate too.
Yeah.
If the standard deviation was, say, instead of 98, let's say it was 20, that's kind of a moderate standard deviation. Do you see that?
Mm-hmm. Okay.
Yeah, a good question though. So the important thing is to understand it. Okay, so there's our car salesperson. Let's see, I think I have another example, but we only have so much time in these webinars, so I can't do too many examples. But lots of examples happen. Okay, life insurance is another one where if you are an actuary, I don't know if you know what that job is. Anyone know what an actuary does? Similar to broker, somewhat. Yeah, they decide on how much money to charge for insurance. That's what an actuary's job is. And to be an actuary, you really got to understand expected value because you're going to have to decide what that fee should be so that the company's expected value is what they want it to be. Do you see that? And that's what an actuary does. And that's, insurance. All right, so then the next biggie that comes from discrete distributions is called the binomial distribution. That's a special kind of discrete distribution. So here's the definition. A binomial distribution. By the way, hopefully you all know what the prefix bi means. What's that mean? Yeah, two. You've all seen a bicycle, I hope. It means there's two wheels on a bicycle, right? So binomial means there's two answers. Okay, often we just call it yes or no, but whatever there's two answers, and there's only two answers to every survey question, two possible answers. So a binomial distribution comes from multiple independent trials of a yes/no question. And the yes/no question can not necessarily be yes/no. It can be two answers, and you can turn it into yes/no. Does that make sense? So as long as there's just two answers, okay? And measures the number of yes answers. Okay, any questions on that? So let me give you an example that doesn't come from, this is like my webinar is already pre-printed, but I got a new one. Sorry, I don't want to destroy your day, but it's depressing. And that is, in any given year, what do you think the probability is that that year worldwide is going to be in the top 10 in average temperature for high average temperatures, and since recorded history? And recorded history is 1880. You could say 2022, but we weren't recording average world temperatures in the year zero. In fact, remember if you lived in America, you didn't know Europe existed. If you lived in Europe, you didn't know America existed. wherever your ancestors might have come from. So 1880 is actually when world average temperatures came up, where they started recording. Just so you know. And by the way, today I looked online and because I didn't know, so I went online and it said 1880. Okay, and 2022 hasn't existed yet. We're in it, but we don't know what the average 2022 temperature is going to be because it's only January. Okay, so first thing, from 1880 to 2021, how many years are there? And one way of doing it is you can go 2021 minus 1880. gives you 141, but it's a little tricky. It's actually 142. Because, for example, from 2020 to 2021, there's 2 years, but they subtract to 1. Okay, so 142. So that's the first thing to note. Okay, so by the way, so a question I have. So there have been 142 years in recorded history. Of global temperatures. Any questions on that? Okay. All right. I did tell you that this is going to be a little depressing. So let me go to a website. And this is Climate Central, which looks pretty trustworthy, by the way. I don't think they're like, cheating or anything like that. And if you look at the 10 hottest years on record globally, so that's our average annual temperature. Okay. You'll notice, for example, all 10 of them have occurred in the last 20 years. Do you all agree from looking at this graph? So here's the 10, and the most recent, the longest one, the one that happened, in farthest ago history was in 2005. Last year was not the hottest. 2016 was the hottest. Okay. Again, but last year was pretty darn hot. Okay, so in the last 20 years, 10 of them have been in the hottest. I mean, in the last 20 years, 10 of them have been in the top 10. Any questions on that? Okay, so let's suppose we do the following. Let's think about the following, and let's look at it. In the next 20 years, if the weather is random, find the probability that at least 10 of them will be in the top 10 of the prior 142 years. Right? So maybe it's not that unlikely, right? What do you think? Do you think if you randomly select 10 years, okay, so the next 10 years, for example, and it was truly random, you think it's pretty likely, 20 years, sorry, we're going to randomly select 20 years. Do you think it's pretty likely that 10 of them will be in the top 10? Any guess? Not seeing I'll jump in, but let me explain. So this is an example of a binomial distribution. And we're assuming randomness. Okay, so we're going to be a climate change denier. That means we're going to assume, it's just random, that just happens, right? And that's because for each year you look at, it's either in the top 10 or it isn't in the top 10. Is that clear? That's the yes, no question. For every year you look at, it's a yes, no in the top 10 or not in the top 10. And what we're going to be looking at is the probability that at least 10 of them in the next 20 years would qualify for the top 10 from what we've seen in the last 142 years. Any questions on that? So the first thing is our N. N is our sample size. We always use the letter N for sample size. There are certain reserved letters in statistics. N is one of them, mean sample size, which is equal to 20. Because we're going to pick 20 years, next 20 years we're going to look at. And then we need to go probability of a yes. Okay, so for any particular year, what's the probability that that year will be in the top 10? Okay, this is actually quite simple, but you know, the word simple is all depends on the person, right? So I'm going to make an equation. I'm going to make a fraction. Remember, probability is a fraction. And again, if we out of 142 years, how many out of 100? This is a really stupid question. How many out of 142 years are in the top 10 of the 142 years? 10. Do y'all agree that's a stupid question as it gets? Of course, it's 10 because there's 10 top 10s. And it's out of 142. Any questions so far? Now, 10 out of 142, let's work this out, is, I'm going to round 0.07 is probably good enough. That's actually good 3 decimal places because it's a 0 after that. So 0.07. Any questions so far? Okay. And we want probability that X is greater than or equal to, I think I can actually make it happen. There we go. The probability that X is greater than or equal to 10. Any questions on what we want? At least 10 means greater than or equal to. So, by the way, there's a lot of math involved. Why should you smile if I tell you there's a lot of math involved? Yeah, it means you could just use a calculator and not worry about the math. Okay, there's all kinds of factorials and stuff like that, which I'm not going to talk about. But now we can go in here. Remember, 0.07 is a probability of yes. So let's go back to the calculator. And guess which calculator we're going to use? What number? 7. And of course, a big hint is I'm doing this in order. I made these calculators in order of the class. So number 7. All right, so in order for X to be greater than or equal to 10, what's the smallest number it could be? It's not a hard question. 10. 10 is the smallest number greater than or equal to 10. What's the biggest number it could be? $20. Because remember, we're looking at 20 randomly selected years. And so the next 20 years, you want to say if the next 20 years would qualify for the top 10 over the past 142, there's only the highest number you could get is 20. And that would be if all of them were high. Number of trials is 20 because we're checking out 20. The P was 0.001. 0.07. Any questions on that? Okay, and you might be surprised to see the answer when I hit calculate. Here it goes. So I want to let you know what this means. Does it mean it's impossible to happen because the probability shows 0 on the calculator? Yeah, it doesn't mean it's impossible. What it means is that the calculator can only handle so many decimal places. And it basically is all of the ones it can handle are 0. So it's like 0.0000000. It's like 8 decimal places or something like that of zeros. So pretty much it is almost impossible for this to happen. Okay. By the way, what do you think the probability of, instead of having at least 10, how about at least 1? So if at least 1 of 20 years, that would change everything. And that would mean the low is now 1. And if I calculate that, it's about a 77% chance of having at least 1 out of 20 years being the hottest in the top 10. Do you see that? And you can play around and see others. This is an example of a binomial. So again, it's a yes, no for each year. Yes, it's in the top 10, or no, it's not in the top 10. And we're looking at a bunch of years, and it's how many were yeses. And it's a probability of that. Any questions? Any questions on this example? Okay. And again, in these webinars, I only have so much time to, so I give you like one main example per shot. And since it was so easy to change it to a 1, I can do that and call it 2 examples, but there's really only 1. But there are lots and lots of times when you want to find out binomial distributions. Okay, anytime, yes or no. So for example, if you're working in a hospital and you're dealing with cardiac arrest, what's the big yes, no per patient? Died or not, okay? Very much yes or no, okay? And what you want to do is you want to make sure that the probability of a large number of deaths is small. Do you see that? So, and I don't work in a hospital, so I don't know the percentage of people who come to the emergency room with cardiac arrest and die, but that can be found, and you can find out what the probability of having this amount. So if you're going to have some new procedure, what you're going to do is you're going to see if that probability or that percent is reduced, and what would the probability of that reduction be under random chance. And if that probability under random chance of that reduction is small, then the FDA approves it as a good procedure. And that would be an example, because I know we have some people that are interested in working in a hospital. And that would be an example of how things get decided on. And that's how they get decided on. Okay. All right, let's go to the next chapter. And that is continuous distributions. So continuous distributions. Continuous distributions, again, means that you can't list all the answers. Okay, so it is any number on a number line or in an interval of a number line. There's like an infinite number, uncountable, you just can't even list them. And that makes it continuous. The true definition, by the way, it's too hard for this class, but I want you to just have a feel for it. That's all I care about. Okay, and what I like, and I actually didn't learn this until I actually taught English in Japan, believe it or not. And then I had to think about it, and because they don't have these two words, these two phrases, and that's how much and how many. How much, most questions that start with a how much ends with a continuous answer, right? How much do you weigh? You might say, exactly, how much do you weigh? You might weigh 149.3721 ... pounds. Do you see that? You can't list all the possible answers. Whereas how many, how many siblings do you have? Okay, can you list all the possible siblings that people could have? Yeah, and I want to remind you those can't be fractions. right? So including myself, there are 4.5 siblings in my family, but that's because I have a half sibling. But the point is that you can list all the possibilities. So if you can't list all the possibilities, you can't make a table. Got it? Because the table involves a list. So you do a graph. And this is, who remembers what this curve's name is? What's the shape of this curve? Came from chapter 2. Bell, but what's the statistics word? Bell curve is the general word. What's the statistics word we use? We're going to have chapters on this. Remember? Normal. Normal. It's not a hard word, but it might be hard to remember. It's called the normal curve. Okay. So one of the things about the normal curve is it's very complex in its mathematics. So it's not where we're going to start. Instead, we're going to start with what's called the uniform distribution. But we can look at a normal curve and we can say the probability of being between two values under a continuous distribution. For a continuous distribution, you can draw the graph, is going to be the area under the curve in between those two values. And that is going to be the definition of probability for a continuous distribution, is it's the area under the curve between those values. You do not know a formula that gets you the area between two values for a normal curve. Okay. In fact, Mitt Braulio might not even know the formula. It's very brutal. He might involve power series. It's a really brutal thing. So you don't have to know the formula. When we get to the normal curve, that's the old "you trust me" and the calculator. So we're not going to start with the normal curve. We're going to start with something you do know how to find the area of. Tell me what you know how to find areas of. What's the easiest that you know how to find an area of? Yeah, rectangle. And when you have a rectangle, that means the curve is flat, right? It has a flat top. That's the definition of rectangle, isn't it? So when it has a flat top, we're going to use the word uniform. So a uniform distribution, and we'll say from A to B, because you have to have a low and a high for a uniform distribution, is a distribution such that any two given intervals of length k, whatever that length might be, that is contained in AB has the same probability of occurring as any interval of occurring, and any interval outside of AB has a 0 probability. So for example, if I told you, let's say if you go and you looked at, say, large eggs, how much does a large egg weigh? Right, because there's medium, large, extra large. Just give me a guess. I need a number. What's your guess on what a large egg might weigh? Not seeing anyone guessing. 4 pounds? Wow, you're really thinking a large egg. Yeah, definitely not. Let's type it in. It's definitely not 4 pounds. Weight of a large egg. Okay, here we go. Oh, this is perfect. So large eggs are between 63 and 73 grams. Okay, by the way, that's not 4 pounds. So that is much lighter than 4 pounds. Okay, I don't think there are any eggs of 4 pounds, dinosaur eggs maybe. Okay, but a large egg is between 63 and 73 grams. So I'm going to use grams because that's what the internet told me. All right, and we're going to assume, which may not be right, I'm not an expert on eggs. We're going to assume that those are uniform. Okay. So what we can say is that if you have a uniform distribution between 63 and 73, that means that the probability of a large egg being, say, 60 grams. What's the probability of a large egg being 60 grams? The hint is it's very easy. It's 0. Because if I told you I have a large egg in my hand, what's the probability is between 60, that it's 60 grams? Well, it has to be 0 because if it was 60, it wouldn't be large, it would be medium. Do you see that? So if you're outside of the interval, the probability is just 0. And in fact, even if I said what's the probability that it's between, say, 50 and 60, that's still 0 because there are no large eggs between 50 and 60 grams. Do you see that? Because they have to be between 63 and 73. Okay. Now here comes a tough one. What is the probability if I randomly select a large egg that it's exactly 70 grams? Large eggs are between 63 and 73. This is a tough one. It's kind of tricky. It's really easy if you understand it, and it's tricky if you don't. Okay, 111, I can see you guessing that. Okay, the probability of it being exactly 70 grams is 0. And the reason is in between 63 and 73, there's a continuous distribution. There are an infinite number of different weights it could be. One of those weights is 70, and 1 over infinity is 0. So anytime you need to find the probability of being exactly a certain number for a continuous distribution, the answer is always 0. Okay, any questions on that? On the other hand, let's do another example because I actually have it drawn. Let's do a math question. And there's a big suppose. Okay, suppose that the time students spend with a math tutor is uniformly distributed between 10 and 120 minutes. Okay, which is probably wrong, but whenever I say suppose, that means just buy it in the problem, but don't use it in life. Got it? Okay, so I want to show you a couple things. One is the notation. And that is, we almost always use X for the variable. You've seen that before. Then comes this guy. Okay, and by the way, this is the shift button next to the 1. Who knows what that's called? Sometimes I get no one who knows what that's called. It's on your keyboard. You could look at it. Hey, somebody knows. Tilde. Tilde. It's also, if you know Spanish, it is the symbol above the ñ, if you speak Spanish. And what I've learned is Spanish speakers usually don't know it's called tilde. For some reason they don't have a letter, they don't have a word for it or something, but it's called tilde. Yeah, yep. Yeah, it's that one, and you can see it here also. It's, again, it's just to the left of the 1 on the keyboard and a shift. So that means has the distribution of. So we can say the variable X has the distribution. And what do you think letter U stands for? That one's not tricky at all. Uniform, yeah. So U stands for uniform. So that we say that X has a distribution that is uniform between 10 and 120. Any questions? Any questions on that idea? All right, so now here's the first question. If a randomly selected student who used a math tutor is observed, find the probability that the student will spend between 30 and 70 minutes with the tutor. All right, so what we do on this one, the very first step is we draw the picture. And uniform distributions, as we said before, are rectangles. Got it? So I'm going to draw an x-axis. I'm going to draw a rectangle that starts at 10 and goes to 120. We don't know how high it is. And in math, when you don't know something, you give it a letter. And I like to give h for height. You can use whatever letter you want, but h seems good for height, and make a rectangle. So let me ask you, are there any questions on drawing this picture? Okay, now we want to find out the probability the student will spend between 30 and 70 minutes. So I write probability that x is between, oh, there should be 30, sorry. Oh, sorry, not yet. We want to find that out, but what we do know is the probability that x is between 10 and 120. Right? Because if it's uniform between 10 and 120, that means there's a 100% chance that if you randomly selected someone, they're going to spend between 10 and 120 minutes with the tutor. That's what that means to say low and high. So that means the probability between 10 and 120 is 1. Got it? Okay, now the probability is the area under the curve. Now, if you have a rectangle, the area of the rectangle is the base times the height, which I'm using BH. Stop me if there's anything you don't understand. Okay, the base is 110 because that's how far it is from 10 to 120. You can actually just subtract 120 minus 10 is 110. Times the height. So now we know that 1 is 110 times the height. And we want to solve for the height, so you divide both sides by 110, and we get the height is 1 over 110. Are you starting to see some algebra? That was a promise I made at the beginning. We got a little algebra today. Nothing advanced, but you have to be able to do basic algebra. Any questions on getting the height? Okay, the height is not the probability, but if you don't know the height, you're not going to get the probability. Okay, so now we need to find out what is the probability the student is going to spend between 30 and 70 minutes. So what we do is we look at the picture again, but now we shade in between 30 and 170. Do you see that? And the probability is the area of the shaded in rectangle. So the probability that x is between 30 and 70 is the base times the height, because it's still a rectangle, and areas of rectangles are base times height. And then the base is going to be 70 minus 30. The height we already found out, that's why I had to find that out, is 1 over 110. So we can say it's 70 minus 30 times 1 over 110, which is 40 over 110. And if you want a decimal, you can drop in a calculator if you want. Any questions on how I arrived at that answer for the probability for a uniform distribution between 110 and 120 of an event being between 30 and 70? Any questions at all on this example? Okay, so the next question is find the first quartile for the time that students spend with a math tutor. Okay, who remembers what first quartile means? That was chapter 2. Chapter 2 is an important chapter, by the way. Yeah, that's the first 25%. What that means is that the probability of being in the first quartile is 0.25. Is that the same thing as the lower 25%? That means that your probability of being there is 25% or 0.25. So that's really important to understand what first quartile means in terms of probability. So once we know that, now we can draw a picture. So we have the same picture. We're between 10 and 120. We have our H, and our H, by the way, is 1/110. I could have put that in, but I left it as H. This time we don't know the value on the x-axis. What we do know is the area. Probability is area, and we know that the probability is 0.25, or the area of the rectangle is 0.25. So let me stop and make sure, are there any questions about this picture? Because you're responsible for knowing how to do your own picture for uniform distributions. And by the way, if it doesn't have the word uniform, don't draw a rectangle. That's a mistake a lot of people make. Okay, you have to see that word uniform. All right, so now we're able to create the answer. So the area is base times height, area of a rectangle. The area of this rectangle is 0.25. That's given. So I write 0.25 is equal to the base. Well, the base is how far it is from 10 to x. That's the base of this left rectangle. And to find out how far this is from 10 to x, it's very simple, but you have to know what to do. It's going to be x minus 10. Just like over here, to find out how far it was from 30 to 70, we did 70 minus 30. But now we have an x down here, so it's x minus 10. The height is 1/110. We already figured that out. The same rectangle. Okay, now we have to do what's called algebra. And if you have this and you have a times, you get rid of the times 1/110 by multiplying the left and right hand side by 110. Right, multiplying by the denominator gets rid of the denominator. So then I can say 0.25 times 110, that's multiplying the left-hand side by 110. And then if I multiply the right-hand side by 110, it's gone, and I just have the x minus 10. Any questions on that? Again, we want x by itself, and if you have an x minus 10, then how do you get rid of the minus 10? Add 10 to both sides. So we add 10 to both sides, and we get 0.25 times 110 plus 10 is equal to x. And I put the x on the left. Doesn't matter which side. With equal, you can put it in either directions, right? So then the rest is boring calculator work. Stick in 0.25 times 110 plus 10. Okay, and by the way, you're always allowed to use the calculator. You can use the one I've got where it says click to see the regular calculator. You can always do that. It's on the bottom of every one of them. And you get 37.5. Always a good idea to look back and say, does that feel about right? Right, if you got 98, you should worry. That's not the bottom 25%. Do you see that? So 37.5 looks about right. It's on the low side between 10 and 120. Any questions at all on this example? Any questions? Make total sense? Okay, it seems like I've done a lot. Let me tell you the big difference between last week and this week, though. Last week, I did some examples, and then you look at other examples in the homework, and they look totally different, didn't they? This week, I did like 4 examples, and everything you look on your homework is going to look just like those 4 examples. Okay. Now, they're not going to have math tutor and students and all that. That's just extra words. But if it's uniform and you want to find a probability, then That's this first example. If it is uniform and you're given a probability and you want to find out a value of X, that's the second example. Any questions on these two examples? And similarly, there's expected value and there's binomial distribution, and they all look like the two examples I gave. All right, now there's one more type of uniform distribution question, and that is the mean and the standard deviation. So the good news is the mean might be obvious. If the distribution is uniform between 10 and 120, how do you think you would find the mean, the average in this rectangle between 10 and 120? The hint is it's obvious. Yeah, you average 10 and 120. And remember, the average means you add, don't minus. Right? The average of two numbers, you add them up and divide by 2. Do you remember that? Yeah, so we average, you add them up and divide by 2, and that's the average. Average is the mean, and it works. Any questions on that? All right. Besides the mean, what's the other big statistic? I said that the biggie in this class. Median's a nice important one, but it's not the biggie. Yeah, standard deviation. Remember on your project, you're required to have a whole paragraph on standard deviation. Okay, median, you'll probably have a sentence. You see the difference? Okay, so the mean and the standard deviation are the two most important statistics in this class. The other important one, which we talked about today actually, is proportion. And that comes up a lot. Not for uniform distributions, but it does come up. It comes up in binomial and in a whole lot of other places. But for uniform, mean and standard deviation is what you're required. So here comes the big theorem. And that is, let's suppose X is uniformly distributed between A and B. Then the mean, remember we use letter mu for mean. You add them up and divide by 2. That one we guessed. The standard deviation, I guarantee none of you would have guessed this. Am I right? Is the square root of B minus A quantity squared over 12. Okay. Are you responsible for having this one available easily for you guys on the exam, for example? The answer is no, you need to have this one. But are you responsible for knowing why it works? Like deriving it? The answer is absolutely not. Okay, that would be a good actually challenge question for me to give Braulio. And I'm not even sure if Braulio would get it right. He might, but it's pretty brutal and it involves a lot of calculus. So we're not doing it. Right, but you might want to jot it down on a little note card that has all the important formulas. Okay, you may need the mean, but you may be able to just remember that one because that's just the average of the two numbers. But it can't hurt to put it on a note card. Standard deviation, you don't want to have to memorize this. And you will not derive it. So, but it's an important one. All right, so now here's an example. And let me read it. Suppose that the number of ounces of water that people drink from a drinking fountain is uniformly distributed between 1 and 8 ounces. Okay. By the way, suppose means I made it up. And that the number of ounces of water that students use to fill their bottles, which by the way, just before class, but I think I need it now. That's what I did. I filled this bottle using we have a bottle filling drinking fountain. And that number of ounces of water that students use to fill their bottles in the drinking fountain is uniformly distributed between 4 and 16 ounces. Again, suppose means I'm making it up, but you can handle that. Okay, you watch Thorn take a 2.5 ounce drink out of the drinking fountain, and Preston fill his water bottle with 5 ounces of water before he runs off to class. Okay. Whose water usage is more unusually small compared to the rest of the people who use the fountain for the corresponding water usage? Any questions on the question? Okay, now when you want to find out how unusually big or small something is, the z-score is our statistic to find out how unusual something is. Do you remember that? Okay, and then the big formula, that's a good one. Yeah, again, there is a program that does z-score, but this one's so simple that it's worth it to know. And it also tells you what it's about. And that is that z is x minus mu over sigma. Okay, so you see how far it is from the mean, divide by the number of standard deviations, and that shows you how many standard deviations away you are from the mean. And that is a z-score, which is a measure of unusualness in this class. Any questions at all on the goal here? Okay, so once we have that, let me do that so we can see the work. Then we work it out. So what I'm going to do is I'm going to just do Thorn first. Then I'm going to do Preston. Thorn, it says, took a 2.5 ounce drink out of the drinking fountain. And for drinking fountains, they are uniformly distributed between 1 and 8 ounces, because that's what it says. So I'm going to write x tilde u 1,8. Notice we're not looking for a probability, we're looking for a z-score. So it's not, we don't need to draw any rectangles on this one. Then I'm going to plug in. Our mean, mu, is the average. That's 1 plus 8 divided by 2. Any questions on that? I'm going to make that bigger because I think it might be too small for you to see well. Does that help? So the mean is 1 plus 8 over 2. And put in the calculator in your head, whatever works, 4.5. The standard deviation is, again, the square root of b minus a quantity squared over 12. So it's a square root of 8 minus 1 quantity squared over 12. And trust me, you don't want to do this one by hand. You want to use a calculator. And I got to 2 decimals, 2.02. Any questions on this? All right, so then we find the z-score. So the z is x minus mu over sigma. X, Thorn took 2.5 ounces. So that's 2.5. Minus 4.5, because that's mu, divided by sigma, which is 2.02. In your calculator, by the way, if you can use a calculator, don't forget parentheses around the 2.5 minus 4.5. Because you have to force the order of operations. That's important for calculator work. And that's around -1. Preston, same idea. Preston did the bottle. And for the bottle, that was uniform between 4 and 16 ounces. So I'm going to write x tilde u 4, 16. The mean will be 4 plus 16 over 2. Let's make that bigger. 4 plus 16 over 2, which is 10. 4 plus 16 is 20, over 2 is 10. The standard deviation will be 16 minus 4 quantity squared over 12. And then all of that, take the square root of. And I put that in my calculator, and I got 3.46. All right, then we go ahead and we put that into the z-score formula. So Z for Preston is going to be Preston's ounces. Preston filled 5 ounces of water. So I put 5 minus the mean. Mean was 10. Divided by the standard deviation. The standard deviation was 3.46. Pop that in your calculator. And you get negative 1.45. Remember, Z is a measure of how unusual something is. If it's unusually small, then it's a high negative number, okay? If it's unusually large, it's a high positive number, okay? High meaning far from 0. So which is more unusual? Yeah, Preston. Preston's more unusual, okay? By the way, Thorne and Preston were students in my class, in my stats class. And I thought that was a cool name. So any questions on this uniform distribution and how to use the mean and standard deviation?
For the sigma calculation, is it always b minus a squared over the number 12?
Yep.
Okay, that's just the standard formula.
Yep. And if you know calculus and you come to my office hours, I can prove it for you. If you don't know calculus and you come to my office hours, I can give you misery because I can't show it in a nice way. Even if you know calculus, I'd probably be giving you misery, by the way, because it's a pretty brutal proof. Pretty cool though, if you love math and you know calculus. Yeah, so this is one of those, it's just a formula. Let me pull it up. There it is. And it's always that, okay? It's good thing about formulas is that's the good thing about math. Math never changes. 1,000 years from now, that's still going to be the formula for the standard deviation of the uniform distribution. Okay. All right. And then the very last thing is a secret word. And the secret word for today is many. Because if you remember, that's one of the key things that you have to put into the conclusion or the explanation of what an expected value represents. Many was one of the big words, because you're looking at many different types of things. Okay, and in fact, I'll give you a just something that happened to me once. I taught a class called Mathematics of Gambling, and I taught how to figure out the probabilities of winning and losing and what's good games, what's bad games, and how good and all that. And I did the expected value of blackjack, okay, for a few things. And then I had, during break time, a student came in and she said, I work at the casinos, and over the last several months, the casinos are not winning money at the table. And if you know about casinos, many games are played at the casinos in a couple months. Do you know what I told her? Yeah, I said, look at your camera, go back, watch the camera, and you're going to see that whatever was happening was not playing by the rules. The next day, the news came out, and there was a syndicate, and they all went to jail because I taught, and this person wasn't just a worker, this person was in charge of the entire operations of the casinos in the northern, in our area for that particular company, but took my class because couldn't figure out what was going on. So that was an application of expected value So I guess there's some people, maybe I shouldn't say too loud because those people might get out of jail and kill me, but but I feel good that I stopped cheating because cheating shouldn't happen. So that was a use of expected value. And again, in months of playing at the casinos, that's many, many, many gains, which means that it is very, very, very likely that on average, the win for the casino will be, and then it was about 8% is the way they had it. And I helped them with that 8% too, as in I helped them with the rules to make it 8%, to make that expected value 8%. Just to give you an idea. So that's an application that I personally was on both, did twice. One is to make the 8% happen by helping with the rules, and the other was to catch the cheater. Okay, or show them there was a cheater. Because it was kind of like the climate change. It was pretty much a probability of 0. So that's all I have to say. Let me stop my share. And let's stop the recording. Just a second. There, now I can stop the recording. There it is.